a new packet. So, do you need a new packet? Yeah? Or do you have it? I need it. Okay. Pardon me, Lex. Thank you. Does anybody else need a packet? That was the homework, too. Okay. That was the homework from before break. Okay. All right. So today we are looking at the perpendicular bisector theorem. So our topic today is to apply the perpendicular bisector theorems. We have two theorems we're looking at today. I was supposed to do the whole thing, but then this morning I was like, yeah, that's enough. Okay. So we're going to get through about half the notes, get through about half the homework, and we'll just finish it up tomorrow. Okay. All right. So, again, I'm going to be using some colors here. We're going to read very carefully. This turns out to be really quite easy, but I want you to really see the picture that's going on here. All right. It says, if a point lies on the perpendicular bisector of a segment. Okay, so interpreting that first line according to this picture, I have a segment here. I have segment AB, so it is my segment, and I have this point C, which happens to be on this line CD. You can see that it has arrows. It goes on forever. It has a right angle. What does that tell me of that little right angle box? It's got to be perpendicular, 90 degrees, perpendicular to the segment. So that's the perpendicular part. And these little tick marks tell me what? That they're the same, that it must have bisected then, that segment. So CD is the perpendicular bisector of that segment, okay? And that point then, point C, is equidistant from the endpoints. So the distance between C and A happens to be the same as the distance to endpoint B. Which is like all well and good and stuff, but the real point is that this is a perpendicular bisector that goes on forever. So I'm going to extend this line, make it really big, and so I can say, hey, I'm going to put another point on there. What if I put a point here on the perpendicular bisector? I'm going to call that point, not D, let's call it, let me give it a G. There we go. That's horrible. There we go, G. Pretend that's a G. Okay. Point G is on a perpendicular bisector. So what must be true? AG is congruent to GB. It's equal distance from the endpoints, okay? And I can put another point on here. Hey, there's point Z on my perpendicular bisector. What do we know? ZA is congruent to BZ. Okay, so do you see this like bridge I'm building here? It's just getting taller and taller. So anywhere on a perpendicular bisector, that point is going to be the same distance to either endpoint of your segment, okay? Which is kind of a neat thing. All right. That's a great way to tell if something is perpendicular. You're building something and you're like, hey, is it really straight up? You measure from one point to the end of the wall and one point to the other end. It should be the same, okay? All right. So then we also have a converse. If a point is equidistant from the endpoint, so here we have our point C, and they're showing us here that it's equidistant from the endpoints, and that's what these markings are telling me. I'm equidistant. That point C is the same distance from A as it is to B. If we're equidistant from the endpoints, then I didn't fill that out, I forgot. Then that point C must be on a perpendicular bisector. So if CA is equal to CB, then CD is perpendicular to segment AB. So CD is perpendicular to AB, and it bisected as well. So AD is congruent to DB. If we're equidistant, then we're also bisected, sort of one way to think about it. Okay. I didn't fill it out up here, I forgot. If we're perpendicular and bisected, then we're equidistant from the endpoint. So then CA is congruent to CB. Sorry, I didn't write that down. Forgot. Okay. Basically, lots of things are equal, which is kind of nice. So let's look. We're going to figure out if we're on a perpendicular bisector and therefore equidistant, or if we're equidistant and then bisected. So let's look here on number 1. What information are they telling me in this picture? What markings did they give me? Perpendicular, yeah, we got a perpendicular, and so this would be a perpendicular bisector. Perpendicular bisector means that we are equidistant from the endpoints. So we have 7x plus 24 is going to be equal to 13x minus 48. We're equidistant to the endpoints. Well, maybe I could do a therefore equidistant. I don't know. How do we solve for x? Take away the 7x. Okay, I'm going to subtract 7x. Gives me a 6x. So 24 equals 6x minus 48. Then what can we do? Add 48. Beautiful. So we have 72 equals 6x, and then divide by 6. So we get x equals 12. Beautiful. All right, let's look at number 2. Slightly different picture. What are they telling me in this picture? Yeah, the hypotenuse is, yeah, there you go. We are equidistant. Equidistant from the endpoints, which means we must be on a perpendicular bisector. So we got the perpendicular part, but we got to have the bisected part. So those two little segments are going to be equal. So what equation can we write? Good. 17x minus 3 equals 9x plus 13. Good. Do we need to solve for x? We're good? Okay. All right, you can go ahead and do that later maybe if you want to. But you'll definitely do it on your homework. Okay. RS. We have to find RS. Again, in this picture, I can see that I have a perpendicular bisecting a segment. So they're giving me that perpendicular bisector. Can't spell. If I have a perpendicular bisector, then I know that I'm equidistant from the endpoints. So what equation can we write? What equation should we write? Thank you. 7x minus 22 equals 4x plus 5. This kind of looks like a cell phone tower, or imagine like a flagpole. And these are like the wires that hold it upright. It does kind of look like a sailboat, So, but imagine if this is like a pole, then these are the wires are going to be equal. All right. Let's solve for x. What do we do to solve for x? Minus 4x, so that gives me 3x minus 22 equals 5, and then add 22, so 3x equals 27, and then, good, divide by 3, we get 9. Are we done? No, what do we need to do for this one? Find RS, very good. That extra step for RS is right here, so we're going to plug in 4 times the 9 plus the 5 gives me 41, very good. All right, over here in this picture, it tells me if you imagine my wires are congruent, the distance to the endpoints is congruent, which means I must also have bisected segments. So 2x plus 11 must equal 14x minus 37. And we can solve for x. We don't need to do that right now. And then figure out EG. One more step to plug in and find EG. All right. Are these all seeming like the same thing? Setting them equal, right? Not too bad. All right. Number 5, once again, the wires holding up my pole are congruent. Then we must also be on a bisector, a perpendicular bisector. So what equation would we write? Mm-hmm. 5x minus, good, equals 3x plus 17. They are, in fact, equal. All right, if we solve for x, we would get 14. And I'm just going to jump through that. How do you find A, B? Plug it into both of them and add them up? Sure, we can absolutely do that. 5 and plug in the 14 minus 11 plus 3, plug in a 14 and add 17. That is absolutely a way to do that. There are many ways to do that. We do get 118 if you were to do that. There is more than one way, okay, but that's an option. Okay. Last one here, what's the equation? Sorry, not last one, almost last one. We have a bisector here, perpendicular bisector, which means my wires must be equal. So 6x minus 26 must equal 3x plus 34. And again, you can solve for x, but then go one step further and get j, okay? Not a problem. All right, any questions on these? No, pretty good, right? All right, last thing. Very last thing, number 7. We're going to finish these notes tomorrow. So here, we're asking a question. Determine if L lies on the perpendicular bisector of segment JK. You'll notice that they gave me ordered pairs. And so I'm going to be doing something with a formula involving numbers, okay? We actually are going to need to use the distance formula here. So the distance formula we're going to write down because we have not done this in a very long time. So it's a good review. The distance formula we have been using on Delta Math mostly. So we've been just drawing triangles and simplifying it using the Pythagorean theorem. Leg squared plus leg squared equals hypotenuse squared. This is the same thing. Comes from the same place. The distance formula is a big giant square root. We're going to take something, square it, and add it to another thing that's going to be squared. And since we're dealing with ordered pairs, we're going to subtract some x's. So x2 minus x1, quantity squared, added to y2 minus y1 quantity squared. So that is the distance formula, and I'm going to show you how to work through that one more time today. But I do want a little picture here. So it says, is L on a perpendicular bisector of segment JK? So right off the bat, they're telling me that we have this segment JK. And the question is, if L is hovering around somewhere, we want to know, is it on a perpendicular bisector? That's the question. In order for it to be on that perpendicular bisector, my wires holding that up need to be congruent. So JL, we want to know if that's the same as LK. So are the wires holding up our light posts, are they the same? And if they are, then we're on a perpendicular bisector. So we're going to do that. We're going to figure out the distance between J and L. So I'm going to do that. JL, so using point J and using point L, I'm going to use my distance formula. I'm going to set it up with a big square root and some bubbles being squared and some bubbles being squared. I need to subtract my x's here. What are the x's I'm using? -9 and -7. So -9 minus a -7. I also need to subtract my y's in this bubble. What are the y's we're using? 2 and -8. So 2 minus a -8. Very good. Okay, I'm going to work through this a little bit. -9 minus a negative is really plus. Good. All right. What is -9 plus 7? -2. So this becomes -2 quantity squared. What is -2 quantity squared? +4. Very good. -2 times -2 is always going to give us a positive result. If you get something negative, you did it wrong. Okay, it should always be positive because we're squaring the whole thing. 2 minus a -8 becomes plus. That is 10. 10 squared is 100. All right, so we have 4 plus 100, which is equal to the square root of 104. All right, we also need to find the distance between L and K. So LK, I am going to do the same thing, except now I'm going to use point K and point L. Same thing. So squaring something and squaring something. What are the x's we're going to use here? -9 and 1. So -9 minus 1. And the y's? Two and 4. So 2 minus 4. Good. All right. -9 minus 1 is -10. -10. -10 quantity squared is 100. And then we have 2 minus 4, which is -2. And -2 squared, +4. So we get 104. Are the lengths the same? They are. Yes, they are the same, which means yes, we are on a perpendicular bisector. Do you have questions for me? Okay. You guys today just need to work on number 1 through 9 today on this homework.